architecture supporting rapid algorithm development.
Good afternoon. Today I'm going to talk to you about a concept, a concept that will support virtual, flexible computing architectures that will help the development of algorithms to be implemented in production a little bit faster than they are today. So what we have here on the screen is a perfect environment, really, and this is modeled after the systems development lifecycle. And we want to be able to plan, analyze, and design our code, our implementations of our programs to support data processing. So normally in action, this is hard to achieve for many reasons, and we'll look further into that. So what we do today is we want to take the code from development, and then there's a transitionary period where the code is prepped, things are wrapped around the code and get it ready for production. And then once the code enters production, there are some certain requirements that are needed for that code to adhere to. Then there's security concerns, there's proper application resourcing, application script preparation, and in some cases there's a need to do application porting. So many of these things should be taken into account before it actually goes to it transitions to production. But these are the things that we're running into today. So a closer look at the problem, kind of break out some of those topics you last saw. So under security, compliance is very important, especially when you go into a data center, and security has become a big issue in data centers today. So looking into an application and the way it's developed is very important that the security compliance is inserted in the beginning. Also, CPU architecture, memory I/O, the big one there is really CPU architecture. And as we see on the end there, we have three types. So the code could be developed for a particular architecture which doesn't exist in production, which causes money issues, delays, and if these things aren't considered in the beginning. So you definitely want to identify your target architecture when you're moving your code through its process. Also, we want to take into effect automation, so logging, monitoring. These things are very important, especially when you're dropping a piece of code into a production environment, because once it enters into the production environment, these are all the things that a support staff will need to maintain and make sure that that piece of code is maintained properly. So the solution, one of the solutions to those problems is server virtualization. Starting off, server virtualization is a set of files, actually, let me back up. Server virtualization is when you take a piece of hardware and you're able to make multiple operating systems in that piece of hardware. And then the end result of making those multiple operating systems in that piece of hardware is a set of files. So what you see here is multiple virtual machines utilizing the physical hardware of one server. And moving forward, taking that concept a little bit further, we can begin to make virtual appliances. The virtual appliances are virtual machines that have a specific job. So these virtual appliances can be lean, you can only add software to these virtual appliances that will be needed to do whatever job is necessary. So in this particular scenario, we want to make a virtual appliance for code or a virtual appliance for processing data. And once you do that, you want to take into account what you need to put in that virtual appliance. The libraries, any third-party software, any logging, any security software that you want to put inside that virtual appliance to help your application run better, run smoother, and make that virtual representation of an OS and a server lean and able to do its job, and also meet the requirements of its target architecture. This goes the same for if you're going to create a data processing virtual appliance. So in action, what we would do is take this virtual appliance and transition it to the production arena. So one of the other problems that I mentioned earlier was application resourcing. So oftentimes we don't know what the application is going to do when it goes live. So the resourcing of the application becomes a problem because if it goes live and there's not enough resources or the timeliness requirements around delivering product to the community is not enough, then we're stuck with what we have in a traditional environment. So when we use server virtualization, we can tweak those resources, whether that be I/O, storage, CPU, memory. We have the ability to tune the resources to produce the product in the timeliness that we needed to begin to share with the community. Also, server virtualization will allow us to share our work with the community. Some of the presentations before me have touched on different ways that we can share the work with the community, science algorithms, data products, and all these things kind of come together. But now, when we're talking about sharing the code and sharing the resources to actually process that code, server virtualization makes it kind of easy to begin to push a standard installation out to the community so that the student or another professor at another school can download that set of files, apply some resources to it, and then begin to use it immediately. So, it makes it easier to begin to share. And then how we do that is we would package up our installed virtual appliance, post it to a web server, and allow the community to download it, edit it, post it back, and then begin a series of collaboration so that things can improve. So what you see here is a graph that kind of shows traditional versus virtual server computing. And what I really want you to focus at is the time to production. So if we do some of the things that I mentioned before, where we have a virtual appliance, and we do some of the pre-work and planning that goes into putting code into production, we'll see a decrease in time in actually getting that code to a production environment, because the things that must happen in order for a code to run successfully in a production environment and be maintained really increases the time of that actually happening in a traditional environment. So many of the things that we have to do as an end result of operating in a traditional environment can happen beforehand in a virtual server environment. So in that way, you will have your production code go into live action faster. So putting it all together. So what we will do is we have to decide which type of virtual appliance we want to make. And then the next step is identify our target architecture. And that's a very important step, because we don't want to do any reporting, which will cause a longer time for us to get to production. And then we have to select the software we want to install to make our virtual appliance or development environment very lean. We want to build, test, and finalize that appliance so that we can provide some documentation and instructions around what it will do, how it does what it does. All these things kind of go into and meet compliance vectors for security. So once we have all these things in line and we follow that process down to transition into production, we'll have a smoother process, and all our components will be in place to actually maintain and support that piece of application. Are there any questions?
You identify Power, Spark, and x86, whatever, as your three principal hardware elements. Have you actually implemented virtual machines on all three of those?
There are virtual machine or virtual server platforms for x86, IBM Power, and Spark. There isn't a virtual platform that covers the gamut of OSs on the Spark platform.
Okay, and a follow on, what sort of a performance hit are you taking for virtualization, say, for Power?
In the IBM arena, actually none, because you have a different. The way they do their virtualization is you can do it direct, and they have their software kind of built into their platform. Normally, you take about a 3 to 6% hit when you're doing a virtualization on x86 platforms. But we're hoping to adjust for that by the hardware being faster. So today, if I run in a traditional environment, 6 minutes, and I have and I take that traditional environment, put it in a virtual environment, just by the advancement of the hardware, we hope to adjust for that 3 to 6% decline in processing time or extra time, by newer hardware.
How do you expect your hardware to provide that when hardware is not getting faster? It's going parallel and it's getting multiple cores. Those cores are running at the same speed or slower than the current hardware is, and the virtual machine is generally assigned to a single core. You can't take advantage of the other cores for that virtual machine.
Well, in some instances, right, and so they're making hardware that actually takes advantage of the virtual technology. So it allows the virtual machine that direct access to the CPU. And then also with today's OSs, you can have virtual machines with multiple CPUs, larger memory amounts. So as the technology improves, your flexibility in that environment will get better, and your processing times will get better. So in some instances, virtualization might not be the answer. But when we're talking about being flexible and being able to adjust for certain environments, I think it's a very good architecture to go with.
This is a very important topic, and thank you for your presentation. One of the things that you did was to judiciously avoid the mention of any specific commercial or public domain implementations of these concepts. Quickly, could you comment on your experience using some of the readily available tools like VMware, VirtualBox, whatever it is that you found that allows you to do this successfully?
Sure. What we have in production today at ESPC, we have IBM virtualization, where their version of it is they have a VIO server that kind of handles the hypervisor or scheduling of access to the CPU. I have a project that's currently being built today, and we use Zen, which is the Red Hat version of virtualization. So the benefits that you get from, and the next step is VMware, right? So VMware is like the Cadillac of all virtualization softwares. So the benefit that you get with the VMware is that you have all the tools there that allow you to do some of the cool things with virtualization that you would like to do. But Zen is another software that allows you to do some of those things also, but the tools aren't there. So, and that's the key thing is the tools that are applied around that particular solution. But Zen, why we chose Zen is because of the cost benefit for us, and it was less of a skills change for us because we are a Red Hat shop. So we already know how to use the Red Hat technology. Zen was a pretty good fit, and also is a cost benefit for us because on top of the virtualization platform that we used, which was Zen and Red Hat kind of bakes Zen into the OS so that any virtual machine that we build on top of that, we don't have to pay for it license-wise. So it works out very well for us when we're talking about 26 clustered processing nodes. And it also allows me to be flexible. And also the question that the gentleman asked back here, well, some of those answers are yet to be seen, right? So our mitigation point for processing time and I/O on the questions he asked about hardware is just that we'll include more of it. So so I mentioned earlier about tweaking the virtual machine to whatever the process requirement is. So I have the ability to do that in a virtual environment. So whereas in a physical environment, if I undershoot or overshoot my resources, it's pinned to a virtual to that physical machine, and I can't do anything else with it. So, are there any more questions?
Thank you very much.
Thank you.